welcome to AstroNight. So who is here for their very first AstroNight? Wow, welcome. I hope you enjoy it. You come back for many more. So right now we're going to raffle off our t-shirt. So everyone get your tickets out. And I'm going to read off the last 4 digits. Okay, so the last 4 digits are 4372. 4372. Lucky winner? No? Lost your ticket? Okay, I guess we'll draw another number then. Get your tickets out again. Hopefully you didn't tear yours up. Okay, the last 4 digits are 4334. Okay, hey, there you go.
Okay, so welcome. I'm very happy to introduce Emmanuel. So Dr. Emmanuel Fonseca. Can you hear me? Yeah? Yeah, okay. Emmanuel got his PhD in Vancouver, UBC. He's specializing in the observation of pulsars and how you can use them to study gravity, basically. So tonight, Emmanuel will talk about the history of gravity and general relativity. Thank you.
Okay, can you hear me? Can you, someone in the back, can you hear me? Yes? Oh, thumbs up, that's good. Hello friends, welcome. As Emily said, my name is Emmanuel. I am a postdoctoral researcher here at McGill University. And so what I wanted to talk with you all today is about general relativity, about gravity in general, but talk about the history. I feel like there's a lot of really interesting, the history of science in general is very fascinating for all kinds of reasons. And I think general relativity is no exception, given a lot of the news that's been buzzing around over the last couple of years. And even just in general, having been in this field with so many for so long, there's a lot of neat things to learn. So obviously we'll be talking about Albert Einstein, right? The man himself. But I think one of the many things I want you guys to take away is that Einstein wasn't the only one who worked on these problems. In fact, there were quite a few things he resisted, and I hope that is clear as the talk goes along. So please get ready. Some of these concepts may seem advanced, and I'll do my best to explain them in an accessible way. And of course, at the end, if you have questions, let me know. So, but first, what I want to do is set the stage and give some context in terms of what brought about this big revolution in the early 20th century. Was Einstein just kind of sitting in his apartment or in a cafe and just figured everything out? Or were there things going on before his time that kind of caused people to move in the direction that we're in now? And the answer is yes. So again, for some context, in the 17th century, Isaac Newton came up with his own theory of physics and gravity. We call it Newtonian Mechanics nowadays. And this is the physics that you learn in your first year, second year of university. The idea that the same force that pulls an apple from a tree to the earth is the same one that causes the earth to go around the sun and the moon to go around the earth and so on. So he was able to kind of quantify those things in a way that others were able to find useful. And how useful was that? To give you a sense of how powerful his framework was, astronomers for some centuries even were noticing that when you applied Newton's ideas to orbits, like the orbit of the Earth around the sun and the other planets, things seemed to check out, which was great. But there was something really weird going on with the orbit of Uranus. And as time went on and people refined their measurements, people were convinced something was going on, something weird was happening with the orbit of Uranus. And so people took Newton's ideas, they took his equations, and they applied it, and they said, okay, given the fluctuations that we were not initially expecting, the only thing that could be happening that could be relevant is that there's some other planet farther than Uranus that is causing its orbit to do that. There's something perturbing the orbit from the outside. And so these two theorists, John Couch-Adams and Urbain Le Verrier, learning French, so I probably butchered that, but they actually independently, theoretically figured out that, okay, if there is a planet, it must be of this kind of mass, it must have some amount of stuff, and it must be at this part of the sky at this time of night. Sure enough, astronomers, when they saw their studies, they looked at the part of the sky and they found Neptune. So this was a dramatic demonstration as to the power that these kind of physical theories have. Before, it was just astronomers looked in the sky, found something, studied it for a while, and then classified it. These guys really started this revolution of, well, why don't we use the theory to explain something that initially doesn't seem to make sense? And sure enough, they found a planet with that description, which is really neat. But there were a lot of problems that were kind of gradually discovered as time went on. So like I said, Newton's gravity is sufficient to describe the orbits of planets as shown here. Things go around each other with some period at some rate. And they were able to apply that for all the orbits except Mercury's. So what astronomers noted over time is that the orbit of Mercury is shifting. It's not a perfect ellipse. It's an ellipse that itself will shift over time. And this effect is called orbital precession. And people came up with all kinds of theories. They even posited that there was some planet really close, like really close into the sun, that was perturbing Mercury's orbit. They even called it Vulcan. You know, it was actually a very real thing people considered in the 18th century, but they couldn't reconcile it with other observations of the other planets. So they said, look, there can't be a planet in there. We don't know what's going on. This is one of the first of several black eyes in Newton's theories. And the major kind of like nail in the coffin, the final thing that made physicists in the 19th century go, okay, this isn't working, was this experiment set up by Albert Michelson and Edward Morley back in the early 20th century, late 18th century, late 19th century, which is now famously called the Michelson-Morley experiment. It's one of the most famous experiments in all of physics. At the time, people were saying, if Newton's ideas are really correct, there has to be this thing, this what's called a luminiferous ether, within which light will propagate. So there's this absolute thing that we're all moving around in. And they wanted to figure out ways to detect that absolute thing, okay? And so what people said, eventually theorists said, you know what, like the way we're going to make that work, the way we can test that is see how the speed of light changes as the Earth orbits the sun. And so they designed this experiment. They called it an interferometer, kind of like neat little diagram shown here. And they said, okay, if the speed of light really does change because we're moving in this ether, then we should see that with this experiment, the details of which I'll go into in a little bit. They ran their experiment several times, and they found that, no, the speed of light is actually constant. It does not change at all. They repeated this experiment over some years, and sure enough, they still said, no, we're finding that the speed of light is the same. It's one of the most famous results in all of physics because it's basically just was the final thing to say Newton is not right, or his theory, his ideas are incomplete. Okay. So that's sort of like the vague context in terms of what really started the revolution in physics at the beginning of the 20th century. So Einstein was this sort of young patent clerk by the time he graduated from university in Germany, in Zurich. And he started to kind of think about these things privately. He was very famous for having these what are called thought experiments. He imagined what would it look like to me if I was traveling along a light ray, close to or at the speed of light, that kind of stuff. And so between 1900 basically and 1905, he was starting to kind of formulate these ideas and trying to figure out mathematically, how do I alter, what do I need to change, how do things change so that these things kind of work out and you have this consistent set of physical ideas. And so he basically was the champion of this, as hopefully will be clear in the talk. But like I said earlier, he wasn't the only one. Something that's not commonly known is that his first wife, Mileva Maric, shown here, is sort of noted by historians to having helped him with his ideas. He was the main driver among all theorists and all people, but he had a lot of help. And his first wife has been credited recently by historians as actually having helped him kind of suss out some ideas that were all in his head at the time. And what wound up happening was in 1905, he published a series of papers, 4 academic studies that we now physicists refer to as I'm going to say this wrong, Annus Mirabilis, I think. It's sort of it's a German phrase for what's called the miracle year, because each 4 of those papers had long-standing, long-term impacts in the field of physics. 2 of them actually had to deal with what is now called special relativity. So this is the precursor to the general case. So one of those 4 papers just kind of presented the framework. It was like, oh, okay, like if I alter, if I introduce these notions, we can recover these things that seem paradoxical for so long. And so that first paper was basically the outline of the laws of special relativity. And then the second paper highlighted a very interesting result of that first relativity paper that showed that you can have this equivalence with mass and energy. And that's arguably one of the most famous equations ever, right? Has anyone not seen it before? No, right? Yeah, so it's one of those things where it was something that is so simple, but again, dramatic. Because according to Newton, energy is only ever associated with motion or interactions brought about by forces and interactions between things. Einstein said, no, you can actually have this inherent amount of energy in stuff itself. There's this equivalence between mass and energy. And so that really sort of changed the game, but very slowly. That's the thing I also want to highlight, is that progress in physics is very slow. So according to Kip Thorne, who's a very famous modern-day theoretical physicist, Einstein was so excited. He was so supremely confident that he was like, "Oh man, people are going to go nuts. I'm going to get so much attention. It's going to be great." Hence, he was smiling. And after about a month or so, obviously this was before computers and planes and stuff. So news took a little longer to travel, but it was still fast enough for him to be like, "All right, within a month, I'll just get all these letters in the mail." So after a month, he was like, "Well, I haven't really heard anything from all my physicist friends, people, the news, nothing, right?" So he was like, "All right, why not see what happens after 2 months? Surely 2 months is enough, right?" No. People were still not really reacting to his ideas. So at the very beginning, at the onset of his proposals, people were not really tuning in that sense. They weren't really seeing what he was seeing, because again, progress in physics is slow. You really need experiments, you need observations, you need nature in order to kind of verify your ideas. So it actually took a year or two really for people to kind of hone in and be like, "Oh, okay, like these ideas kind of make sense, they're really interesting, it's a really different way of looking at how the nature of time and space, how those things work." And sure enough, it wasn't until 1907 where this very famous mathematician, Hermann Minkowski, pointed out, he said, "Look, Einstein's equations actually directly suggest that space and time are unified. You no longer treat them as solely different things. You can think of them as like this 4-dimensional, what he called space-time." So the phrase space-time didn't come from Einstein, it came from this guy, basically. And then that's kind of when the theorists and some experimentalists at the time were like, "Oh, okay, like that's actually kind of interesting. There's an elegance to it for sure, but it's also very easy to use then." And so there's this very, very famous quote that had come out at the time when Minkowski was presenting his ideas, saying, "The views of space and time which I wish to lay before you have sprung from the soil of experimental physics, and therein lies their strength. They are radical. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." It's a little poetic for sure, but the idea there is that people were starting to realize at that time that Einstein's ideas were really different. They were radical. And as I'll talk about later, they were so radical that some of those ideas Einstein himself did not believe in. We'll get there in a minute though. So, like I said earlier, Einstein was not the only person to really kind of tackle these problems. Again, once the trains started to move and people started to take it seriously, he actually needed help. There's a very famous adage, or something that people kind of loosely hear about, that Einstein was bad at math. I mean, it's not wrong in the sense that, yeah, he had help from famous friends of his, Marcel Grossmann and Michele Besso. Marcel Grossmann was a mathematician. He actually was the one who suggested to Einstein, "Hey, there's this really advanced set of mathematics that could actually be very useful for your theory. It seems to describe curvature really well." And this was prominent when you wanted to incorporate gravity, because the reason why special relativity is called special is because it kind of addresses things in physics but avoids gravity altogether. It ignores gravity. That's why it's called special relativity. He wanted to generalize his theory so that it also accounted for the effects of gravity. That's why it's called general relativity. And at some point he realized, man, I really need to know math better. But at the same time, Einstein was a pretty smart guy. I mean, he was pretty good at math, okay? Like, it wasn't necessarily something that, he wasn't like an actual bad mathematician. It was just, the level of math that was needed to describe his ideas was really, really advanced, and these two guys really, really helped him out. with that. So sure enough, after a couple of years of development, he was able to actually put forth these ideas, but he had competitors. I'm sure you can probably imagine physicists, really, really intelligent, kind of intellectually engaged people, are very egotistical. They compete against one another. There's a lot of glory involved. Usually it's friendly. It's almost hopefully friendly, but there's a lot of racing in terms of, you know, who can get to the key ideas first. And Einstein himself was really worried that someone was going to beat him to the punch. There's a very famous mathematician, David Hilbert, who impacted all kinds of realms of mathematics and physics in the early 20th century, who actually, historians point out that he was the first one to figure out the math that Einstein needed to implement. And at the end of the day, Einstein was able to formulate his theory of gravity with a singular equation. I don't know if you guys remember that drawing I showed at the beginning that had F is equal to ma. That's sort of the key, one of the key equations for Newton's theory of gravity and mechanics in general. And this is sort of a similar importance. These are called the Einstein field equations. Everything comes from here. And so Einstein and David Hilbert independently battled one another to find out what do those equations look like, and they both settled on this. And technically, some people argue that David Hilbert was first. But again, Einstein was the key driver. He's the one who laid the physical intuition for that set the stage for relativity in general, which is great. So again, one of the key things that relativity kind of just throws open in general is the idea that you no longer describe gravity as this force that acts at a distance between two objects. It's instead the warping or the curvature of what we call spacetime. It's just this warping of time and space in such a way where things are no longer interacting through a force, but there's this curvature that things move around in as well. And so that's why you tend to, whenever you look up gravity or Einstein or general relativity, you'll see pictures like this of like these warped spaces where the curvature is really extreme at the points where there's stuff, mass, suns, stars, and all that. And then from this, we're able to kind of describe all kinds of physical scenarios in a way that in some ways is consistent with what Newton had proposed, but proposed additional things as well. And that's what I'm going to get into now. So people like to glorify moments and things. And when it came to testing Einstein's ideas, there's a series of moments in the history of physics that are referred to as the classic tests of relativity. And so what do I mean by that? So like any good theorist, Einstein really wanted to verify that his theory was the right one and that the superior one. And what people needed to do in that case was to see, well, okay, his equations will say things about nature. Does it match up with what we observe in nature? So again, take, for example, the orbit of Mercury. It was observed to precess, as we say. It was observed to shift systematically over time. And it wasn't clear, and we knew for a fact that Newton's theory could not describe that precession. There was something missing. There was something missing from Newton's ideas. And so sure enough, Einstein took his theory of gravity, applied it to orbits, and said, okay, look, let me see what the equations that describe orbits look like when I use the theories of general relativity. And sure enough, he was able to find an additional amount that caused the orbit to precess. Turns out that according to general relativity, orbits naturally precess. They naturally change with time. And so among the theorists, among the physics community, this is what made him famous. He was able to solve a 300-year-old problem, basically, with those ideas. And again, that's the key test here, is that you can come up with whatever idea you want, but it has to match up with reality. It has to match up with things that are seen and observed by everybody. And this was sort of the first test. This is referred, because it was the first one, because it was a problem that was known about for so long. And he was like, okay, and even in private letters and so on that he wrote to people, he even pointed out, like, whatever idea I come up with, it's got to predict this. It's got to make sense of this problem. And he made sense of it. So again, that made Einstein famous among the physics community. People were kind of taking him seriously already, but that's kind of what elevated him to superstar status in the physics world at that time. But he then proposed a second test. So when he co-founded his field equations, as we call them, he set out these series of tests. He said, hey, look, my theory checks out with Mercury's orbit. Oh, one thing I noticed as well when I apply my theories of gravity to the sun is that it predicts that light that travels near the sun will appear to bend. And what that means is that if you have a star that to us is really close to the sun, the light rays that are emitted from the star and come to us will actually, the trajectory will actually bend slightly. And what that leads to is that it causes the star to kind of move and jiggle from its true position to something close by, but not quite where it actually is, on the sky, right? So the idea is that, like, as the sun appears to get closer and closer to a star, the star's position will move a little bit, okay? And it's a tiny amount. But he said, look, in theory, it's possible to do this at some point. We just need to figure out ways in which to do this. And sure enough, there was a famous astronomer at the time, Frank Dyson, said, hey, look, guys, I mean, we have these natural phenomena called solar eclipses. How many of you actually saw the one in August? How many of you actually came out to McGill? Oh, a few of you. Okay, cool. So we had a lot of people here at McGill. So it wasn't totality. But people said, look, if you can go to a spot on the Earth where there's a total eclipse, where all the light gets blocked out, you can actually point a camera and see stars. It gets that dark, okay? And so that's what Frank Dyson had proposed. And sure enough, Frank Dyson, along with a very famous astronomer, Arthur Eddington, said, you know what, let's mobilize, because there's one coming up. In 1919, Einstein proposed his tests in 1915, I think, at the end of 1915. So he's like, all right, guys, this is going to happen in 2-3 years. We need to act, and we need to plan this so that we can actually make this measurement. So sure enough, 4 people, including Frank Dyson and Arthur Eddington, went out into 2 groups, groups of 2 people. One went to the islands of Principe and the other of Sobral, and they both independently made measurements of the sun when it reached totality. Because again, you probably were wondering at the beginning, how can I look at the sun and see a star at the same time? That's crazy, right? But again, the solar eclipse is what helps you, and this is the image that Arthur Eddington had taken from Sobral, I think. Or no, sorry, Principe. So sure enough, they went, they made these measurements, they took these photographs, they figured out, okay, here are the stars whose positions we know during the night sky when the sun's far away. So as the sun appears to approach the position of those stars, they actually measured the deflection. They said, oh no, actually the position is actually shifted by a measurable amount that was entirely consistent with Einstein's prediction. So sure enough, the second test, the second classic test, passed. So again, the first test, the one with Mercury, made Einstein famous in the physics community. And this second test basically just made the world go nuts. This is the thing that made Einstein famous. So all the major news outlets at the time, the New York Times and all that stuff, went ballistic and were like, holy cow, this guy figured this thing out, that's crazy. And that's where his like rise to stardom came from, was this second test. Because people just found it really fascinating. And sure enough, why not, right? That's a really neat, non-intuitive thing that his equations predicted. And we see this effect all the time, along with Mercury's precession. We don't just see it in our solar system, we see this all over the place. And so when we take nice, pretty images with massive optical telescopes, or telescopes of all kinds, we see these effects out in nature, out in different parts of the universe. So it's a very ubiquitous thing, and it, again, more observational evidence that Einstein, if not fully right, is on the right track, right? Because again, it's all about progress, right? We gotta make moves and push forward. So, again, those are the classic tests. Those are the things that he was able to figure out on his own, exploring his equations and being like, hey guys, check this out. Others said, yes, sweet, right? So, worked, right? But now my favorite part, this is where it gets awesome, is what some theorists refer to as the outrageous legacy. There's even a book called Einstein's Outrageous Legacy that highlights everything I'm about to talk about. So what do I mean by outrageous? So when someone develops a physical theory and certain things check out, like certain tests are passed, things kind of make sense, people start to explore the theoretical landscape. They say, okay, let's apply Einstein's field equations to a star or the Earth or the universe or, you know, all kinds of different scenarios and see what does Einstein's general relativity say about how nature will work in those environments, right? So sure enough, after the few first classic tests pass, people started to do this, like Karl Schwarzschild, shown back here. He was actually fighting on the Russian front in World War I, I believe, when he found Albert Einstein's paper outlining his equations, seeing that the test passed, and was like, okay, let me play with these while I'm like in the trenches. He actually apparently was in the trenches when he started to like kind of dabble in this during breaks and stuff like that. And what he found was really interesting. He said, look, let me apply Einstein's equations to a star, see what the behavior is like. And he actually noted that if you look at the way Einstein's equations describe the geometry and the way gravity works around a star, there's points where the equations blow up. There are points where you achieve what are called these singularities. These points where suddenly just the way that the geometry and the space and time works just kind of blow up to infinities and all that stuff. And this threw everyone out. This blew everyone's mind. They were just like, no way, like that's not real. Generally when a mathematician or a physicist encounters an infinity, usually something went wrong at some point, because like infinity is meant to describe something that's not achievable. It's infinite, right? So to encounter that in a normal scenario like the regions outside of a star was really strange, right? So sure enough, so they call these the Schwarzschild singularities because these are points where the equations blew up. And the most famous one is this equation shown at the bottom. It's called the Schwarzschild radius. And what really threw everybody off was that that value is not equal to 0. For instance, so g and c are constants of nature. The speed of light is c, and g is this gravitational constant we can measure. M is the mass of something. So if you insert, say, like, if you compute this value for the sun, it's like several kilometers. If you compute it for the Earth, it's the size of a marble. Again, you got to remember, this is like 1918, right? So people were just kind of, and science fiction did not exist at the time. So they were like, that's weird, right? The value is not 0. That's what threw people off, right? So believe it or not, people actually debated this, the existence of what we now call black holes, as shown in the background, for 50 years. So from 1915 to about 1960, 1965, the question was, do black holes exist? Do they actually exist? And most people, at least in the earlier parts, were arguing no. And Einstein himself rejected it. He said, no way, right? That can't be real. So what changed it? What changed the reality from do black holes exist to they do exist? Well, in the 1960s, that's when we started to launch things into space on rockets. That's when people started to develop better technologies, more precise clocks, that kind of a thing. And one of the first rockets to launch Geiger counters up into space noted that, hey, there's a lot of X-rays coming from certain parts in the sky. And one of the, not the first, but one of the first objects found was this object that's now called Cygnus X1. It's this really bright X-ray source in the constellation Cygnus that was really bright, so bright that people were like, okay, let's try to follow up and take more careful measurements of the system and what it looks like. And with very quickly, they were able to figure out that Cygnus X1 is an X-ray source. It's very bright in X-rays. It's in a binary orbit, kind of like Mercury and the Sun and all that. And they found that, okay, we can observe one of the stars, and we know that, and we can tell from its spectral properties that it's this massive, kind of a normal star that's much more massive than the Sun. We know theoretically and even observationally that stars of that mass had some size, but the orbit was so small that the other object, the thing that was super bright in the X-rays, had to be tiny, so tiny that there was no discernible size. So this was sort of the first decisive evidence that black holes really do exist. And so what exactly does that look like? Theorists started to kind of rack their brains, and they were like, okay, what on earth could this be? And they said, well, okay, given the proximity, the really tight orbit, and the fact that we can observe the companion star, that big, massive, normal star, we must have scenarios like this, where there's a black hole, and it's actually accreting or adding stuff to it. It's actually tearing apart. It's actually destroying that companion star over time. And the X-rays come from that accretion. It comes from the fact that you have this really intense, extreme environment. Temperatures are insanely high, and sure enough, it's just adding this material over time, right? So this was this was a big deal. This was a big deal because it was the first, surely indirect, but it was the first really convincing non-controversial evidence that black holes are actually real things. And sure enough, this really changed the game. People were starting to take things like this much more seriously. And they're like, oh, wow, okay, cool. And so if you read into the history of physics even more, there's a very famous bet that has to do with the status of this object being a black hole between Kip Thorne, the physicist I mentioned earlier, and Stephen Hawking. You guys have heard of Stephen Hawking, I take it, yeah? So there's a very famous bet. The details I can't go into because it involves, purchasing magazines of different kinds, that kind of thing. But they were like, okay, one person's going to bet that it's a black hole, the other person's going to bet that it's not. But if you read into the history more, they actually both were like, yeah, it's a black hole. Like, it's got to be, right? So it was just kind of like this friendly wager. And sure enough, people actually mimic this with modern astronomical problems. People kind of place bets, like, oh, next conference I'll buy you a meal, that kind of a thing. So it's this fun way of making progress at the same time. So again, I'm not going to like inundate you with equations, but in my opinion, equations are your friends. And I think it's really important to sort of at least show what they look like, right? So Einstein's equation, when it was originally published looked like this in the back, in the black font. And there I show what those different terms in the equations correspond to. So on the left-hand side of the equation, that's the side that describes curvature, the geometry of the space and time that you're considering. That's the stuff that deals with the actual way that space and time behave, right? And on the right-hand side, that's where you actually insert the quantities that describe the source. Like, okay, you're considering a star, so it has a density, it has a size, that kind of a thing. So that's kind of how Einstein's equation worked. But Einstein pointed out, Einstein applied it to something that we would perceive to be the universe and found, oh, hey, like if I was to assume that the mass energy stuff had to be associated with some universe, like something where like the matter is distributed all over and all that stuff, my equations say that the universe should be not static. It should be evolving with time. The size and all that kind of stuff should be changing. And again, remember, this is 1917, okay? They didn't even realize there were galaxies outside of our own, maybe beyond Andromeda. But the word galaxy didn't exist when applied to the galaxies that we know of today. They called them extragalactic, they called them nebula. They didn't even know they were outside of the Milky Way Galaxy. So at the time, there was no evidence that there was a universe even to begin with in the way that we know it now, right? So Einstein thought this was super problematic. He was like, no, come on, no way. Like, that's outrageous. That's silly. Like, there's just no way that the universe is expanding. Again, because everyone thought the universe was our galaxy, people had been making measurements of planets and stars and so on. And what they saw was, no, there's no, like, net expansion. There's no, like aggregate motion that's indicative of an expansion or a contraction. Things are just moving around us and kind of quasi-randomly, or around the galaxy, but like not in an expanding kind of way. So he added this cosmological constant. It's this additional term to his equations. That's not arbitrary. It obeys the mathematics and the calculus that goes into Einstein's equations, but it nonetheless altered or changed the fundamental interpretation of what was going on. He added the constant so that it would essentially enforce a static universe, because that's what we knew. So again, remember, this was like 1917, 1918, right? So a few years later, a bunch of very famous, now famous physicists like Alexander Friedman and Father Georges Lemaitre, like Father because he was actually a priest who actually loved physics as well, and so he was actually working on this problem, said, no, actually, come on, like your equations might actually be right. You could actually be predicting something really interesting here. And they actually were the first ones before Einstein to sketch out what the consequences of those implications are. And he was like, okay, look, there's a really good chance that the universe is expanding and we're just missing some things here. And again, this was all before 1929. But again, the titans of the time, Albert Einstein, Arthur Eddington, all those people were like, just no way, that's crazy, right? So 1929 came around. They built this really lovely big telescope out in California. And Edwin Hubble, who had just arrived at Mount Wilson Observatory, set out to measure, again, what we now can know to be galaxies, but basically made measurements, measuring brightnesses and measuring red shifts, kind of like the shift of properties in the spectrum of these objects that he was studying that indicate speed. And sure enough, he found what the plot on the left shows, which is there's a correlation between how close an object is and how far it's moving away. And the farther it is from us, the much faster it's moving away, indication of an expansion. So it turns out general relativity was correct, but Einstein was wrong. Okay? Again, these are the kind of things I love, because it's just like, no one's perfect, and, it's just one of those things where back in the day before 1929, no one would take you seriously if you said, hey, the universe is expanding. Did you know it? No, everyone would just be like, that's nuts. And again, remember, think about it. There was no science fiction, none of that. This was purely radical stuff. And I love this perspective. It's my favorite thing. It's basically, Einstein figured out through his thought experiments and all that stuff, essentially that the universe was, that there was a universe and that it was expanding, before we humans knew that there was a universe in the way that we know it, right? I love that, just because it's like just poetry, right? So, again, we're physicists. We like to repeat experiments. We like to verify things, especially if they're like really controversial. And so Wendy Friedman and her collaborators back in 2001 used the Hubble Space Telescope, named after Edwin Hubble, and made similar measurements using much more different techniques, but ultimately creating the same figure, and they found the same correlation. And again, this is important because Hubble telescope is obviously great. We're in the area of computers. We're in the era of computer technology, so we have much more refined ways of making these measurements, and sure enough, they're confirmed. So it's just one of those things that speaks to the power of what of what general relativity has sort of given or suggested. So the last thing I want to talk about is this really neat effect called gravitational waves. Have you guys heard of gravitational waves? Maybe raise show of hands. I'm just curious because I know that there was well, most of you, cool. So the gravitational waves has probably arguably the most fascinating history out of all of the major problems with general relativity, because again, around 1917, pretty quickly early on, people were starting to point out to Einstein, hey man, do you know that your equations actually suggest really interesting, weird things going on when things are moving or things are accelerating? They found that his equations were producing solutions, because we solve equations and it's fun. But like they actually found solutions that indicated wave-like behavior. They found what we now call gravitational waves. You have these things that are periodic and they ripple and all that kind of stuff, as shown back here. And again, this was before technology, all that stuff. So Einstein was like, nah, come on, that's silly, right? No way. So, and again, it wasn't just Einstein. Arthur Eddington. There are all these really big names that I'm not even mentioning, like Subrahmanyan Chandrasekhar, whose name I just totally butchered. But there's a lot of really famous people who worked on these problems for many decades. And this problem, like with black holes, only lasted 50 years. People were not really convinced at all that these things existed. So what changed? So again, 60s, good time. People started to finally develop technologies. We were launching things into space. Things were becoming more precise in terms of making measurements. And Joseph Weber was a physicist down at the University of Maryland, and he had done a lot of pioneering work in laser technology. He actually was one of the first people to develop lasers in the way that we use them now. But he wanted to try something else. He wanted to really tackle a different problem that made him really curious, and gravitational waves was one of them. Because again, even by this time, it wasn't clear at all if they existed. Again, at this time, black holes weren't clear to be existed either. They weren't even called black holes. That term came around in 1967, I think. So again, it was just a really different time. But when people mentioned the gravitational wave problem to him, he's like, oh, okay, it might actually be possible to detect these things. And so he spent a few years trying to figure out, okay, how do I detect these things? What kind of things and technologies do I have to develop myself? And so what he eventually arrived at is, again, gravitational waves are the rippling of the curvature of space and time. So if a gravitational wave was to pass by us, space and time would kind of ripple in a periodic way. And what he pointed out was like, well, if I have these like really massive bars, metal bars of aluminum type specifically, then the bars of this size will start to resonate. They'll start to vibrate because space and time around it is actually oscillating. It's vibrating. And so that vibration will be imparted into the bar. And I should be able to measure that vibration. It's basically like a big chime bell, essentially, if you want to think of it like that. So he was actually the first one to come up with this idea. It was quite ingenious, and it started to attract the attention of theorists who were like, huh, that's a very interesting way to try to see them. And so in 1969, after nearly a decade of developing the technology and the process and publishing papers, he actually had announced in 1969 and 1971 that he found them. He actually made measurements that suggested that he detected gravitational waves. But again, like any good physicist, especially if it's controversial, we need to verify the measurements. So people around the world started to actually make their own experiments, also using his Weber bars, and they weren't not able to produce his results. So when enough people did this, they started to realize, oh, okay, maybe he didn't actually detect anything. So, you know, one of the sad ironies is that so Joe Weber passed away in 2001, I think. So this is before they formally discovered gravitational waves. But he actually held on to that. He held to his convictions. He was like, I found them. I know I found them. He had the data. But again, people tried to reproduce the experiment and were not successful. They couldn't see what he saw. But when if you were ever to like Google or YouTube presentations about gravitational wave astronomy and people who were involved with modern experiments, they always credit Joe Weber of being the first person, of being the father of gravitational wave astronomy, because he was the first one who was like hardcore trying to figure out how to see them. And his methods, while not sufficient to see them, were good enough for people to be like, oh, it's actually possible. We can actually see these tiny little things. We just need to figure out a better way to do it. So again, that was over many, many, many years. But what changed? So the gravitational wave game changed completely when pulsars were discovered in 1967 by Jocelyn Bell Burnell. Pulsars, for those who do not know, is this tiny little white dot with light shooting out of it. But in terms of a fun movie, there are these old compact remnants of old massive stars. They're called neutron stars. They rotate really fast, and for reasons we don't fully understand, but we know enough about, they shoot beams of light out of their magnetic poles, kind of like this. So even though we've been able to piece together that they're neutron stars, what we observe is a thing on the bottom, which is like this blip, this profile, this blip of light in the distance. I highly encourage you guys to read into the history of the discovery of neutron stars. It's fascinating. It's a, I mean, in terms of what Jocelyn had to overcome to prove that they're real, this is one of the first occasions where people actually thought it could have been aliens, you know. So it was because it was a really dramatic thing to see out in space. It's just this like persistent bleeping, right? But it's a really fascinating talk for another time. So why are they useful? Here's a map of Boston, Massachusetts, where I'm from. Go Celtics. And the idea here is that you have this neutron star that is really extreme and really small, but really massive. It has as much stuff as the sun, but is the size of a major city. It's extreme as you can get, right? So this is just sort of a comparison of sense of scale. But that's the reason why I love to study them. Emily, who introduced me, studies them. A few of us here study them. They're really fascinating things, and you can probe a lot of different questions about physics and its fundamental aspects using neutron stars and pulsars in particular. So again, how did those enter with gravitational waves? What exactly happened that led them to be very useful and interesting? So in the early 1974, the early 70s, these two scientists, Russell Hulse and Joe Taylor, discovered a pulsar in a binary system. It was the first one ever discovered in a binary system, meaning that these things, this pulsar was going around another neutron star, is what they argued and found. And what immediately caught the attention of theorists was like, oh, wow, that's really fascinating because it's a really tight orbit. It's 7 hours. Remember, it takes the Earth to go around the sun once a year. It takes these two neutron stars to go around each other once every 7 hours. It's a very extreme system. So theoretically, gravity is supposed to be very extreme and very, you know, it's supposed to be very extreme. So people were saying, hey, this is going to be a really interesting system to see things, all kinds of things, the precession of the orbit, especially gravitational waves. And so what they did was they basically observed this pulsar over time for some years, as shown here on the left, and they measured the period of the orbit from the pulsar. Because one of the key takeaways, one of the things that theorists had pointed out was that, well, if gravitational waves are real, then physical waves are known to carry energy, and these gravitational waves will propagate away from the system, meaning that the gravitational waves will carry energy away from the system, and because of that, the system will respond and actually shrink over time. So the orbit will actually decay. We would call it orbital decay. And all they did was, okay, we have this pulsar, let's measure the period. Let's measure the time it takes to go around once. And they did that over and over again for many years. And what they found is that the period of the binary changes in such a way that is entirely consistent with the existence of gravitational waves. So it was so dramatic of a discovery that they actually awarded the Nobel Prize for this in 1993, because it was the first non-controversial, albeit indirect, measurement of gravitational waves. Remember, it's indirect because we're not seeing the waves, we're not seeing the rippling of space and time. All we're seeing is the orbit shrinking, which again, super cool, right? But it's not gravitational waves. And fun fact, do you guys know Vicky Caspi? Vicky Caspi is a professor here at McGill, very visible, prominent astronomer. Joe Taylor was actually her thesis advisor and the advisor of many people who are now very prominent researchers at universities around the world. Nice guy too. So with this, as these things were going on, as these developments were happening in the 70s, people latched on and were like, hey guys, this could be our chance. We could actually find gravitational waves. So Kip Thorne and a bunch of people down at Caltech and at the Massachusetts Institute of Technology, or MIT, came together and proposed to create this radical experiment, which is called LIGO now, which is basically a large-scale interferometer, kind of like the one that I had shown earlier, where basically people shoot lasers and they shoot lights out that kind of split and then come back together. The idea being that if there's no gravitational waves and you set up the experiment just right, the lasers will not interfere with each other when the light comes back. It's basically just a bunch of mirrors at different points, really far away from each other. If you shoot them at the mirrors and the light comes back and there's no interference, you should see this sort of pattern. But if there are gravitational waves, you'll see distinct patterns that people were able to map out theoretically over the years. So they said, look, this is a really good way of seeing gravitational waves, especially those produced by the merging of neutron stars, kind of like the one that I had shown before, the famous binary pulsar one. And so sure enough, they set about doing this in 1976, as over 42 years ago, essentially, at this point. And it was basically this massive long-term buildup because it was a technological feat. There was a lot to figure out. There was a theoretical feat. People only started to really believe gravitational waves might exist like the year before. So they were all excited. It was a totally unexplored space. And as of 2 years ago, nearly 2 years ago even, they actually announced that they had made the discovery. They have two of those interferometers, one in Hanford, Washington, over on the West Coast, and another in Livingston, Louisiana, down south from us. Both of those detectors run independently. They all operate in the same way, but they don't necessarily interact with each other. They just collect their own measurements, and then if they see something, they'll report back to the other and then compare. Sure enough, they saw one reported to the other, and they're like, hey, we saw the same thing. We saw a gravitational wave. And it matched the predictions that people were pointing to. So it was a big deal, because those things showed, for the first time ever, the actual rippling of space and time, something that Einstein, for the majority of his late life, had rejected. And then by the time, before he passed away, he was like, yeah, maybe, you know. He's like, look, it's exciting if we could see it, but it's just way too small. There's no way. Well, we found a way, right? That's what we do. So sure enough, on February 12th, Gabriela Gonzalez and David Reitz and all these really hardworking long-term physicists and astronomers announced, hey, we found them. They showed their data. They published the papers. The community just dove right into it. And they found, hey, wow, like they're right. Yeah, awesome. Like they actually did see it. And it was a really game-changing thing because now we have this era of gravitational wave astronomy. So one question you'll very reasonably ask is, well, how popular was this? It was very popular. Everywhere around the world, people went nuts because it essentially also coincided with the 100-year anniversary of the theoretical discovery of general relativity. Remember, Einstein proposed his ideas in November 1915, and the discovery occurred on September 2015, but then they published them in February 2016. So it was about 100 years afterwards. So everyone went ballistic. They're like, oh, this is amazing, right? But I guess in terms of the outlet that we all know and love and care about, obviously we want to see what the Gazette says, right? But when you go to click on the link, it doesn't work, right? You can find it elsewhere for sure, but the idea here is that people everywhere around the world were like, hey, this is a major breakthrough, this is a game changer. But why is that? Why is this such a game changer? Oh, okay, I'll get to that in 1 second. But again, so LIGO is a long-term, well-planned, several-decade process in the making, right? And it's an experiment that's running right now, or at least it's a project that will run for a long time, and many other countries are starting to get in to that fold and develop their own interferometers to kind of help LIGO and build this worldwide array of interferometers. But there are other ways of detecting gravitational waves too. So when pulsars were discovered, people started to point out, hey, pulsars are really stable rotators. You can time them very precisely. They essentially serve like clocks. So again, that's why we find them useful in general, but theorists even in the 70s were like, hey, you can use pulsars in theory to detect gravitational waves too. And so we actually call this thing a pulsar timing array. It's a simple concept. We basically observe a bunch of pulsars in the sky very, very regularly, and then we kind of see if there's any correlated signature in the signals we get from different pulsars. Because the rule of thumb is that no pulsar is alike. They're all different in their own way. Some are isolated, some are in binary systems, some rotate at one speed, some rotate at the other. They're never the same, and the shapes of their profiles are always different too. But if a gravitational wave passes by the Earth, where we make our measurements, space and time will ripple around our observatories. And so even though we're looking at different things, we should see the same signature imparted in those signals. And that's essentially the idea of a pulsar timing array. And so again, how does this work, right? So if there are no gravitational waves, there's a pulsar on the left, yeah. And then it's rotating, it's kind of bleeping in our direction, and we'll see these very regular signals over time. Again, this is if there are no gravitational waves, right? But like I said, if there is a gravitational wave and it passes by the Earth, what was once regular is now irregular, and that irregularity should show up in every single pulsar. So even though pulsars are not, all pulsars are different from each other, if they show the same irregularity, that's a massive hint that they are that there's a gravitational wave passing by the Earth. And there are very rigorous statistical ways in which we can sort of probe that. And so that's something that a few of us, myself included, work on here. We're part of this pulsar timing array effort, because what is important and what's been pointed out is that, you know, the different types of observatories you have for gravitational waves will allow you to see different sources. So it'll allow you to see black holes. It'll allow you to see merging neutron stars. It'll basically allow you to see things that were once invisible. And this finally ties to, dang it, okay. So, so this was a movie. This is a movie, and it kind of just schematically shows, again, what's going on. We're on the Earth. Our observatories are on the Earth. And there are a bunch of pulsars all throughout the galaxy. We observe them regularly and as frequently as we can. And as a gravitational wave passes by the Earth, we'll see this rippling go on around the Earth. And that'll show up in our measurements for all the pulsars, even though they're all different. And to give you a sense of what kind of observatories we use for the pulsar timing arrays, we use the coolest stuff ever, basically. We use like these really big, massive single-dish telescopes. I don't know if you guys have seen X-Files or Contact or, you know, all that good stuff. Some of you might even recognize things like the Arecibo Observatory, which has been in those films and TV shows. It's still working, even though Hurricane Maria kind of devastated the island. And it actually served as a FEMA center for shelter for various people. So, you know, it's a very prominent, ongoing facility, along with the other ones listed here as well across the world. Finally, okay, cool. So, just to wrap up, why do we care? I'm sure some of you are just like, okay, cool, but why is this important? Why should why should you all care, right? So one thing that's kind of been pieced together over the century, or over the years even, is that the stuff that we see when people take pictures of the night sky with their own cameras, with telescopes, that kind of stuff, we see so many different things, right? Galaxies, stars, planets even nowadays. Like, we can see different things, and that's great, right? But the idea here is that a lot of really recent cosmological experiments have really suggested that those things we see, the things made up of E, but we know that it gravitationally interacts with light, and dark energy, which is responsible not just for the expansion of the universe, but the accelerating rate of the expansion of the universe. So even though there's a lot of stuff out there that we can see with our own eyes or with X-ray observatories, all that kind of stuff, there is a 95% that's invisible. But gravitational waves allow us to see them. And that's kind of why people care about it now. Not just because it's this neat thing that was not predicted or finally exonerated after 100 years of debate, but because they're actually useful. They're useful things for understanding how the universe works, basically. And just a little fun note to end on is that, again, there are these things we're aware of, like black holes and merging neutron stars and all that kind of fun stuff. But we're bound to see like a whole lot of new things that we never have ever seen before. So I encourage you all to stay tuned, because the universe beckons, and gravitational waves will basically allow us to make sense of those things. So thank you for your time, and I'll take your questions. Sure. So that's okay. So the question was: is it possible? Correct me if I'm wrong. If you said it, you asked, is it possible if dark matter could just be something wrong with Einstein's equations? It's a really good question. Believe it or not, there is a community of valid university level researchers who are actively seeking to modify Einstein's relativity. It's actually called modified, MOND, modified gravity, basically, because that's something that some people have pointed out. It's like, hey, maybe Einstein's theory isn't complete. Maybe those equations themselves are not good enough, right? So that's very much a very active and relevant field. But at the same time, Einstein's been so right on in other environments on different scales too, that you know, people are starting to throw other theories into the mix too, like particle physics and all that kind of stuff. So it's clear that there's still a lot of incompleteness with the way we understand nature, but Einstein's theories still tend to work, basically. So that's kind of why there's those different communities, basically. But it's a good question, though, for sure. Question? How can you, okay, so the question is, how can you imagine the amplitude of gravitational waves? So, so for the amplitude of the waves that LIGO detects, so on the on the vertical axis, it says strain and 10 to the minus 21. And what that is a measure of how much space stretches and squeezes, basically. So I think the comparison is your LIGO basically has been designed in such a way that it can detect fluctuations of space and time to the scale of within an atom. So it's a very extreme thing, and that's why people from 1950 to 1960 were like, no way, that's crazy, right? So LIGO's not seeing atoms, but it's sensitive enough to detect those perturbations. And a lot of those 40 years of development from 1976 to now have been spent figuring out what do other things look like? What do earthquakes look like, lightning strikes, all these kinds of things that could add noise to their measurements. They're like, okay, we want to make sure that we see gravitational waves, so we need to consider everything else. Things that we call noise, basically. So that's the scale. It's tiny. But you know, the next time you bolt down Sherbrooke to catch a bus, you're actually generating gravitational waves as you run. Fun fact, you know. So there you go. Another question. I'll take one here. Mm-hmm. Yeah, no, a good question. So the question was, what exactly were Arthur Eddington and Frank Dyson measuring during this total solar eclipse? So the thing they were measuring was the position of stars, basically. Again, like, so when 6 months goes, so later on in the year, the sun will be at a different part of the sky relative to other stars. So you can measure the position of stars at that time. You can even go out now and do that tonight. But they wanted to see, again, the idea isn't necessarily that the light from the sun interacts with the light from the star. It's the gravity. It's the space and time around the sun that causes that bending. So even though the moon had blocked out the sun, the curvature from the space-time curvature was still there, and that's why they had to go during the total eclipse, because during the total eclipse they wouldn't, you know, shoot their eyes out basically by trying to look at the sun, but at the same time they could also make these measurements during a time where the sun was close to the position of the stars in the sky, but close enough such that Einstein's equations would induce those changes that it was predicting. So that's all they did. They measured the position of stars in the sky at different times, and they found that when the sun appeared to be close to the star, the position changed a bit. And then when the sun was at a different point away from the same star, it went back to where it normally was. And that's that gravitational lensing, that bending of light, basically. So that's kind of what is shown here schematically. That's a good question, though. Question? The Weber bars, yeah. That's right. That's true. So I mean, so the thing, so you're right. So the gravitational waves don't necessarily apply forces, but I mean, it's a ripple of space and time, and the bar itself takes up space. So it's kind of the same argument for how pulsars could be used to detect gravitational waves, because we are occupying a space, and if the space itself is rippling, then in theory we can actually see that. Again, it's so tiny that it's something that you would never really notice or care about. But at the same time, that's essentially why they need to use these big, massive, different types of like detectors or apparatus to see those effects, because those things take up space. And if the space itself is stretching and squeezing, then it would resonate somehow, essentially. And that's the idea, is that you have this thing that's taking up space. It occupies a region that will presumably be stretching and squeezing and shaking due to gravitational waves as well. And that's essentially what he was detecting. I mean, I think with aluminum, I'm sure it was a combination of being cheap as opposed to, like, say, steel, for example. But the idea is that, like, there wasn't anything special about aluminum per se. It was just something that was accessible, that was sufficient enough according to his calculations. But again, the idea is that despite his theoretical sort of, despite his work, it wasn't good enough, basically. Question. Is anyone using Weber bars to... For sure. My understanding is that they are not. They're not using Weber bars. They are housed in museums, for sure. I mean, so Joe Weber really did start the field, even though he wasn't able to succeed. But they don't use those today. Yeah. Question? Huh? Yep. So those are good questions. How do people quantify dark matter, dark energy? So the units are percentages. It's just the constitution of the universe. So how, like, what fraction of the universe is taken up by ordinary matter, which are the electrons and the protons, and how much by dark matter and how much by dark energy. So the ordinary stuff we can make sense of because we can take photos of those things. We can use telescopes at different wavelengths and frequencies. With dark matter and dark energy, it's different. It's dark. They call it dark for a reason. You can't really directly see it. Dark matter, like when I showed the images of, so one way they see it is through the lensing, for example. So if you have a bunch of dark matter in the, I think I passed it, sorry. So if you have no, I didn't. If you have a bunch of dark matter in between us and these clusters of galaxies, you'll see the lensing effect. Because again, it's matter that does not interact with light in the same way that like a cloud of gas does. Like light will go straight through it, right? But the gravity around that dark matter will cause the light bending and the gravitational lensing to occur. So that's one way in which we observe it. The way in which it was discovered was by Vera Rubin. She actually basically made careful measurements of how galaxies rotate, how stuff in galaxies rotate. And she found that the rotation rate was totally inconsistent with just normal matter. There had to be more matter than we could see. And so it was a controversial result. People looked at different galaxies and they verified her result. So as more telescopes were being developed, they were saying, wow, this is a really serious problem. There's stuff we just cannot see, but it's presumably everywhere around these galaxies. And that's how we infer dark matter, basically, is through those kinds of measurements. Dark energy, that's a lot more complex. It has to do with the way in which it associates with, for example, the expansion of when people go to make these plots, they actually can infer curvature. So it's not a straight line. There's actually like a slight bend in this relation here. So this is an older plot, but that's one of the ways in which they infer dark energy. And there are more sophisticated experiments that were launched into space that actually made maps of the universe, and so to speak, and actually could infer the amount by which there's dark energy versus dark matter versus ordinary matter. So I'll take, yeah, you had your hand up for a while. The thing, yeah. Uh-huh. Sure. I actually do think I know which paper you're talking about. It's a good question. So basically, does that recent extrasolar object, something that did not originate from our solar system, have an impact on dark matter. I mean, so no, in the sense that even though they are even though presumably that people are arguing that there might be a lot of those kinds of things out there, the amount of dark matter is actually significant. It's like comparable to the amount of stuff in the galaxy, a little bit more. Whereas those objects are not, I mean, they're massive, they're huge compared to like us, for example, but they're not as massive as so they wouldn't have the same net effect that dark matter does. And in that sense, that's how you can differentiate that kind of effect. And again, so the thing is that, like, people point to telescopes to look at this thing. So you can discern you can discern that this is something that is composed of molecules and so on. But with dark matter, it's just such a plentiful thing, and its effects are so prominent that it has to be, that like people are convinced that it's just something entirely different, for sure. One last question. I thought I saw, yeah, go ahead. Do neutrinos have to do with the conformation of gravitational waves? So, a really fun fact. No, for sure. But so I think, so for the first detection, no, basically, because the idea was that they were able to show convincingly that these were two black holes that merged to form a final black hole of some spin and certain properties. But the idea is that with black holes, they're not made up of like normal stuff. They're kind of these really weird, different extreme objects. Whereas there was a recent event that made big news in October that was inferred to be due to the merger of neutron stars. And there the situation is different because you have these things composed of really like high density normal matter, like electrons and protons essentially. There it was different because one of the reasons that event in October of this year was so buzzworthy was because they actually detected the counterpart, as we call it, in normal electromagnetic waves, light, basically. So they pointed their telescopes and they saw these big flashes in the distance that corresponded with the position of the gravitational wave signal. So that was a huge deal. It confirmed a bunch of theories that have been around for 20 years. And in that kind of a scenario, there you can associate neutrinos with interaction of matter and so on. I don't think they did, though, I believe. And I believe that those experiments in the South Pole were running, but they don't say anything for sure. It's a really hard business, neutrino astronomy. I mean, it's totally like prominent and worthy, but it's really hard to measure neutrinos from far away for sure. So, cool. Great. Thanks, guys, for coming out.